In this lecture and the next one, we want to look at an important family of dynamical systems, namely Markov shifts or Markov chains, respectively. Markov shifts are the topological version, and Markov chains are the measure-theoretic version. So in this lecture, we look at topology, so topological dynamical systems, that is subshifts. As usual, for the course of this lecture, we fix a finite alphabet A, and in particular, for this lecture, we assume it's just the numbers from 0 to k-1. Now, a Markov shift, the easiest way to introduce this and to picture it is to think of the set of infinite paths through a finite state system. So that's not quite the same as a finite automaton, as we see in a moment. So you can more think of it as a finite directed graph. So here's an example of such a graph. So the nodes of the graph now are labeled by our alphabet. So to make it easy, we assume the alphabet is just the binary alphabet. And so the nodes of the graph are labeled with the alphabet, and then we just have directed edges between the nodes. And there can be loops on the vertices, and but there also can go between the nodes, different nodes. So the Markov shift induced by this graph is just the sequence of all, or the set of all infinite sequences that we can obtain by starting at any node and then just wandering through the graph following the edges, right, in their respective directions. So we, for instance, we could start at 0, go to 1, go back to 0, go back to 1, stay in 1, stay in 1, go to 0, and so on, right? So this way we would, for instance, obtain the sequence starting at 0, 0, 1, 0, 1, 1, 1, 0, and so on. Another way, we could start at node 1 and just stay there all the time. So this would also be in the Markov shift. Mathematically, a Markov shift can be described using matrices, namely the adjacency matrix. So we start with a directed graph on vertices 0 to k-1. So the graph, the vertices of the graph always correspond to the alphabet, the underlying alphabet. And then we let M be the adjacency matrix of the graph. So that means all entries are either 0 or 1, and we have a 1 entry at the position ij if and only if there's an edge leading from I to j. So we're actually looking at directed graphs, so you should understand this here as an edge from I to j. So let's look at the graph from the previous slide. So here we have the graph. What does the matrix M now look like? Well, we have two states or two vertices. That means we have a 2 by 2 matrix. Right? And here we have in this in the entry 1, 1 gets a 1 if and only if there's a loop going from 0 to itself, which is not the case. So we will have an entry 0 here. But then there is an edge going from 0 to 1. So we have an entry 1 in the position 0, 1. And we have also an entry, an edge going from 1 to 0. So we have an entry 1 here, and we have a loop going from 1 to 1. So this would be the matrix corresponding to our graph. To make our life a little bit easier, we assume that there are no 0 rows in the matrix. So that would correspond in the graph that there are to the fact that there are no dead ends. So assume we had like an additional entry in the alphabet called 2, and then there would be a edge going from 1 to 2, but nothing leading out of 2, that would mean that the second row in the corresponding matrix here, so actually the third row would be completely of zeros. That can be dealt with. It just makes all the arguments a little bit more complicated. So we want to avoid this for now. And hence we assume that every vertex has at least one outgoing edge. So we can actually always find an infinite path, continue on an infinite path. So if we have such an adjacency matrix, like this example M here, then the Markov shift given by M is defined as follows. Well, we can call it X sub M or X sub G, depending on whether we want to emphasize the matrix or the graph. Well, it's the set of all infinite sequences over A, such that for all I, the entry xi sub and xi plus 1 in the matrix, right, is 1. So that means nothing else than just saying, well, whenever I want to pass to the next element, right, in the next entry in the sequence, I have to do so via a connection where there is an edge between from the entry xi to the entry node xi plus 1 in the graph. We can, of course, also look at the two-sided shift based on M in a completely similar way by just looking at the sequences over A to the Z here, so the bi-infinite sequences that have this condition here, not only for all I greater than or equal to 0, but for all integers I. Right? So the first observation we want to make is that this actually defines a subshift. So why is that true? So why is xm defined in such a way as subshift? Well, we first note that it's closed under shift. So why is that? Well, let's look at our example again. Suppose we have a sequence in xm that starts here and then just goes through, follows an infinite path through this graph here, like this 1, 1, 1, 0, and so on. Well, here we started with 0. Now shifting means just we start our sequence we skip the first move and start the sequence at the node 1, right? So 1, 1, 0, and so on, right? So it's clearly closed under shift. The second condition for being a subshift was to be topologically closed. And we want to show this by showing that xm is actually the set of infinite paths through a tree. So which tree are we looking at? Remember in the first lecture on subshifts, we looked at the set of forbidden words that corresponds to a subshift. Now we're actually looking at the set of allowed words. So the set of allowed words is given as u of xm, the set of all finite strings u over alphabet A, such that u is a substring of some x in our set xm. But now, since our set xm is closed under shift, if we see a substring anywhere in some x in xm, then that substring must occur as the first string at some other x in xm, namely the x that is obtained by shifting through this x where it occurs as some substring, right, somewhere, all the way to the beginning. So for instance, if in our example we have the substring 0, 1, 1, right, and let's say we found that it occurs in as a substring in this one, and so on, then it will also occur as the beginning, as an initial substring, as an initial segment of a sequence, right, that we obtain by just shifting this sequence, the first sequence, by 2 positions, right? So we just take this sequence here and shift it by 2 positions, and we obtain this sequence. But this now means we can build up our set xm indeed as the set of infinite paths through a tree, right, where the nth level of the tree is given by un of xm, the allowed words of length n. So let's do this for our example graph up here, right? So which words of length 1 are allowed? Well, that's clear because that's just, we can start at any node, so we can start with either 0 or 1. But now which length 2 sequences are allowed? Well, we could either start at 0 and go to 1, right? So we could go 0 and then go to 1. We could start at 1 and stay at 1. Or we could start at 1 and go to 0. So what we can't do is start at 0 and stay at 0. So that would be a forbidden word. We see that 0, 0 is a forbidden word here, right? So there's no branch here. So these are all at this level, all the words, allowed words of length 2. 0, 1, 1, 0, and 1, 1. And then we can continue this now by looking at the length, words of length, allowed words of length 3, and so on. Right? And we will see that whenever, well, here 0, 0 is the forbidden word, so we cannot possibly extend in with a 0 here. We only can again extend with a 1 here. Right? So, and the set of all sequences in xm, right, is just the set of all infinite paths through this tree. Okay. But as we have shown before, the set of infinite paths through a tree is a closed set, so topologically closed. So xm is topologically closed and hence a subshift. So I would like to state 2 more observations here. The first is that there's a nice correspondence between counting paths and powers of the adjacency matrix. Namely, if I take the nth power of the adjacency matrix, mn, m to the n, so m is the adjacency matrix of the graph G, then the entry ij is the number of allowed words of length n, beginning with I and ending with j. So allowed words now just correspond to paths through the graph, right, the underlying graph. So let's look again at our example graph. Here, this is the m squared, so the matrix m squared. So that should now reflect the number of allowed words, so path of length 2, beginning with I and ending with j, so the ij entry. So for instance, this is the entry 0, 0. There should only be one possibility to go with a path of length 2 from 0 to 0 again. And there is only one going to 1 and back to 0. All right. So there's only one possibility to go from 0 to 1 in a path of length 2, namely going to 1 and staying at 1. Similarly, there's only one possibility going from 1 to 0 in the path of length 2, staying at 1 and then going to 0. But now there are 2 possibilities to go from 1 to 1 in 2 steps, namely going to 0 and then back to 1, or just staying at 1. Right? So this is why we have the 2 here. The other observation is that Markov shifts are shifts of finite type. Recall, finite type meant that there was a finite set of forbidden words. So why is that true for Markov shifts? Well, it's actually the consequence of a rather easy property of Markov shifts. So suppose you have a word u that is allowed. So U0 up to UL minus 1 of length L. So it's an allowed word. And now you want to ask, is U extended by I allowed? Right. And then you can see this is the case. Well, this is allowed if and only if UL and extended by I is allowed, right? Because that's the nature of the definition of the Markov shift, right? So this being an allowed word means you have already traversed your automata that way. Now, if you want to extend this will only depend by I, whether that's possible, will only depend on where on which node you currently are on your path, right? So if you're here, then you can't extend by 0. You can only extend by 1. If you're here, on the other hand, you can extend by either 0 or 1. So that means ULI. So it only depends on whether this block here is a possible configuration or path in the graph. So this means it's true if and only if M, and now with U sub L minus 1 I is 1. Right? But those are just finitely many configurations we have to check now in the matrix. So there's a finite list of possibilities where this is 0. Right here we only have one possibility. So in this example here, we have only we have the forbidden block 0, 0 is forbidden, the only forbidden block. So you can think of these topological Markov shifts as systems that have exactly one step memory, right? So whether you can pass to extend by some element from the alphabet depends only on what you've seen just immediately before that, right? So the last entry here. Now you can think of, you could make this a more complicated system by just making this extension here dependent on, so the possibility of the extension dependent on a number of bits, right, that you see, or number position that you've seen before, right, but still a finite kind of memory. So this way it's possible to define kind of a generalized concept that is called a multi-step Markov shift. So Markov shifts you can think of one step Markov shift, right? Because you only have a one-step dependency here for the extension. But now you can, if you let it depend on, like, let's say 2 or 3 or 5 steps, right, or k, any number of finite steps before, you get the concept of a multi-step Markov shifts. Those Markov shifts are not that easily representable anymore, for instance, by graphs like this. So that's why they're a little bit harder to deal with. But they still give us subshifts of finite type, in particular subshifts. An important topic in the theory of dynamical systems is to find decompositions of systems into smaller systems or parts that are then themselves indecomposable in a certain sense. So just like in number theory, you try to you look at prime decompositions, right, into products of parts that are indecomposable with respect to multiplication, the prime numbers. You can do the same thing often with dynamical systems. So what does this look like, for example? Let's take our old example again, but now extend the alphabet by one further character, 2, and introduce now a new state here that can be reached from 1. But then once we reached vertex 2, we have to stay in it forever, right? So the only way then to extend your sequence, infinite sequence, is just by staying at 2. you can think of this system having two components. The one component where I stay in this part, and then once I entered this part, I always stay in there. So if we have such a configuration here, that means on the matrix side, there are indices ij such that if I take the nth power of the adjacency matrix, the entry ij is 0 for all n, right? That means, graph theoretically, there is no possible path from I to j. So in our example here, there's no possible path from 2, for instance, to 0. If such indices ij do not exist, so graph theoretically, this means that the graph G is strongly connected. That means there is a path from each I to every other j, right, node j. Then the corresponding adjacency matrix is called irreducible. So algebraically, we have that for all ij, there is a power n, such that the nth power of m, the entry ij, is not 0. So there exists at least one path from I to j. Irreducible shifts have some very nice dynamic properties, and I want to point out one of them, namely that they always have dense orbits. So what is an orbit? An orbit of a point is just following its path or route by applying repeatedly or iteratively applying the underlying transition or transformation. So in our case, it's the shift map. So the orbit of X collects all its positions in time under the dynamical system. Right. So in the general setting of a dynamical system, you can think of an orbit like this. You start with X, and then you look at Tx, and then T square X goes here, and then you just follow the orbit around, right, wherever it is mapped. So now an orbit is dense, right, if it gets arbitrarily close to every other point in that system. So that in this picture here, it would mean that eventually our orbit would fill out this underlying space here or set completely. Right. Of course, it does not necessarily hit every point here, because the orbit, as you see, is a countable set, and the underlying space xm is often uncountable. So it's not possible that it hits every point exactly, but it gets arbitrarily close to every point in there. Just as, for instance, the rationals fill out the reals in the sense that every real can be approximated arbitrarily closely by a rational. Right? In this sense, the orbit fills out this space here. So why is it true that irreducible shifts always have dense orbits? Well, the reason is, using irreducibility, we can construct an X which contains every allowed word as a substring, right? So suppose we want to now construct our X, and we want to include a certain allowed word. Well, in my construction of X up to the point where I'm currently am, I'm in a certain state, but now I need to get to a state where I can start this allowed word. But this is possible because I have irreducibility. So that means I can just go to that state where I can, or node where I can start this allowed word. But on the other hand, so every irreducible shift always has a dense orbit. But on the other hand, one can show that if xm has a dense orbit, then it must be irreducible. So why is that true? Well, if the orbit of some x in xm is dense, right, then by our definition of the metric or the topology, well, every I in A must occur infinitely often in X. By our definition of our topology, right, having a dense orbit just means that every possible allowed word occurs in X. That's one of the consequences. But for every I in A, right, there exist infinitely many words that start with I, right? So every I in A must occur infinitely often in X, right? So, but this means we can get from any I in A to any other J in A in the underlying graph G, right? Since X has only allowed words, that means substrings that correspond to paths in G. But this means precisely that G is strongly connected, right? So that we can get from any I to any other J in A in the underlying graph. Hence, the system is irreducible. I want to finish this lecture by looking at a shift, a subshift that is defined on a graph, but not using the vertices as the alphabet entries, but the edges. Here's an example. So the graph looks very much like our previous example. The difference is now that the vertices are not labeled anymore, but the edges are labeled, right? And now the shift, the edge shift given by this graph here, is the set of all infinite sequences that are obtained by just following a path in the graph and noting the edges, the entries or the labels of the edges along the way. So for instance, here I would have the shift, for instance, in a sequence like 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so on. This kind of shift is actually much closer to our finite automaton, because remember we had the notion of a finite automaton or non-deterministic finite automaton, where we just had a number of states and then transitions between the states that are labeled by the edges, right? We're reading the input, so to say. So this way we can interpret this graph of an edge shift as a non-deterministic finite automaton, right? So, and we make this special, kind of a special automaton, by allowing all states to be initial and accepting at the same time, right? So no kind of state is kind of distinguished from the others anymore. I mean, this can be realized by just introducing an initial state and then having epsilon transitions to this, right? As a fully legally defined non-deterministic finite automaton, right? But if we assume now that every state is initial and accepting at the same time, then the set of allowed words for the edge shift corresponds just to the language accepted by this non-deterministic finite automaton, right? So that's because that's just the set of paths through this automaton here. Now a Sofic shift is precisely that, namely a shift where the set of allowed words is a regular language. So you can think of a Sofic shift just given by an edge shift of this kind. So finally note that Sofic shifts are in general more powerful than shifts of finite type. In particular, they do not have to be shifts of finite type. So the example here is the even shift, namely the set of all infinite sequences, binary infinite sequences, so that between two ones is an even number of zeros. And if you look at the previous slide, you will see that the edge shift defined there is precisely represents precisely this shift here, because whenever I want to introduce a zero, the only way to introduce another 0 is to go back over here, or to go there is to introduce another 0. So we always have an even number of zeros once we leave our 1 loop here. But note that the even shift is not a shift of finite type, because we have an infinite set of forbidden words. 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, and so on, right? But the allowed words form a regular language, as witnessed by this finite automaton here.